Hi everyone! Welcome to part 1 of chapter 25. Today we're going to start a chapter on transition metals and coordination compounds. So we've been talking a bit about complex ions, and complex ions are a part of coordination compounds, and they almost always involve a transition metal. So we're going to use this chapter 25 to go a little bit deeper in these areas. So if we look at these two different gemstones, right, on the top we have a ruby and on the bottom we have an emerald, and they're different colors. But actually the thing that's causing the colors in both of these stones is chromium. In the ruby, some of our aluminum from aluminum oxide has been replaced by chromium. So there's some chromium 3+ in there. And similarly, in the emerald, some of the aluminums have been, again, replaced by chromium, but they don't cause the same color. And so it's chromium color causing the colors in each one of these, but what's bonded to the chromium actually has the ability to change the color of the ion, which is cool. Without the chromium, neither one of these would be colored because we don't have any unpaired electrons. Chromium, though, is paramagnetic, and so it's causing these color changes. So we're going to get more into this as we move forward in the chapter. Okay, so we're going to look at transition metals predominantly. We're going to look mostly really at this first row, but we'll look at some of the others as well. And then we'll touch a little bit on the inner transition metals, which is the F block. And they actually sit kind of in the middle of the D block. And so we'll get into those a little bit, but again, we're going to look mostly at the transition metals in this chapter. So the properties of transition metals are really similar to each other. A lot of, transition metals will act similarly to other transition metals, but they're really different from the properties of the main group metals, right? So the metals that are like the alkali metals or the alkaline earth metals, these transition metals are really different. They have really high melting points, super high densities, pretty hard, and they are really good electrical conductors. So they have really specific uses. But the similarity in properties of all of these transition metals comes from the similarities in the valence electron configuration. And so I have here that they generally have 2 valence electrons. And you may be thinking to yourself, well, that's not right. As we go across the periodic table, they're gaining more electrons. And you're right, but if you recall, let's say these elements in this, this top row here, they would have 4s electrons, and then the rest of the electrons are added to the 3d energy level, right? Because the d block is numbered differently. So in reality, they really still have 2 valence electrons in this 4s orbital. So even though we're adding more electrons to the 3d, these 4s electrons are the ones that are really still acting like the valence electrons. So all of them kind of have only 2 valence electrons, even though they're gaining electrons as we go across the periodic table. So this causes them to have kind of similar properties. So all of the transition metals are metals, whereas a lot of the main group elements in each period have both metals and nonmetals. So we can look at the transition metals kind of as a whole, whereas when we looked at the rest of the periodic table, we talked about them more in specific groups, right? And again, these transition metals all act like they have 2 electrons, so they do kind of similar chemistry. What's also cool about the transition metals is a lot of them are colored and paramagnetic. And I remember in college, I was doing some research in organic chemistry, and all of my reactions always came out like brown or yellow, right? These kind of like boring colors. And my friends in inorganic chemistry would get these pretty colors like green and purple and red and really beautiful colors. And it's because they were working with transition metals and I wasn't. So a lot of the transition metal compounds are colored, but it's because they have these unpaired electrons in the compounds, which are causing these colors. So they are paramagnetic. Whereas most main group ionic compounds are colorless and diamagnetic because the metal loses all of its valence electrons. When we are looking at these transition metals, they don't lose all of their valence electrons. They can, but they don't have to. And so they have multiple oxidation states, which we'll get into a little bit later. But so that causes them to be colored, whereas most ionic compounds that we think of normally would be colorless and diamagnetic. That's where we're getting these, like, everything looks like a white powder, right? That would be with the main group ionic compounds. But again, most of these similar properties of the transition metals are due to them having really only 2 valence electrons. So here we go. So again, a lot of them look really similar, right? Copper looks a little different because it actually ends up having one valence electron. Because it has an irregular valence electron configuration, it kind of steals one from the s orbital. But all of the other ones look really similar because they, again, only have those two valence electrons. They are really similar. They have similar properties. So talking about electron configurations, most of the D block elements, they have the same condensed electron configuration. So you find the nearest noble gas that came behind it, right? You put that noble gas in brackets, and then they're going to have some N and then S2. For this first row of elements, this would be like 4s2, right? And we would have had argon in brackets because it was the noble gas that came before. And then remember, the D block is numbered differently. So if this is a 4, then that makes this a 3. Okay, and then, however many over you needed to go in the D block. Let's say we were talking about, I don't know, titanium. So this would be 3D2. Okay, so this X here can be anywhere from 1 to 10, depending on where it is in the D block. And this N value here is anywhere between 4 and 7, because the D block only, or, the ones where we're looking at the transition metals only occur in periods 4 through 7. If you get to periods 6 and 7, we also have to include the F sublevel, those inner transition metals. So it'll go the noble gas, and then the S block, and then the F, and then the D. Okay, and it always goes in that order. When we have this F block, this is going to be N-2. So again, if this is like a 6, this would be a 4, and this would be a 5. Okay. Transition metals, and this is important, okay? Transition metals form ions by losing the electrons from the s orbital first. They will lose them from the s orbital before they lose them from the d orbital, okay? So like if we were looking at titanium here, let's say titanium was going to form a 2+ ion. It doesn't really, but if it was going to, then it would lose these 2 electrons, and it would form this. It would form argon, and then it would be 3D2, okay? And that would be for titanium 2+. Titanium, mostly, though, likes to make 4+ ions, and so it would actually lose all of them, and it would just be essentially like argon, and we would write titanium 4+. Okay, but the point that I'm trying to make here is that if it did make this 2+ ion, it's losing these 2 electrons from the 4s orbital first before it's going to lose any of those d electrons, because that 4s orbital really is the valence electrons, right? So when we're losing electrons, we're going to lose them from the valence shell first, and then we can start taking off the d electrons, which have been added to more of a core energy level. So, like I alluded to earlier, some of our transition metals have irregular electron configurations. And this is because the 4s orbital and the 3d orbital are actually really similar in energy. Okay, the 4s is farther out. It's in the 4th energy level, right? It's a little bit farther away from the nucleus. But the 3D energy level is higher in energy really than it should be. So the 4s and the 3D energy levels end up having kind of similar energy. So electrons can go between them. And so this causes our chromium and our copper and all of the elements below them to have irregular electron configurations. So like normally if we were to write out chromium, it would be argon, and it would be 4s2 3d4. And this would cause it, like if we were to write this out, this would cause it to have this 4s, and then we would have our d orbitals, and it would look like this. So, right, so it's got a full 4s energy level, but then it has like this kind of partially full 3d orbitals. And we know that orbitals are unusually stable, or particularly stable, when they have either half full or completely full sublevels. So instead what we do is we move one of those electrons from the 4s and we stick it in that last 3d orbital. And so when we do that, it looks like this. So now both the 4s and the 3d are half full, which makes it more stable than having this 4s completely full and the 3d partially full. Okay, and the same kind of thing happens with copper. So copper would otherwise have had 4s2, 3d9. So our s orbital would be completely full, but we'd be missing one in the d. And since the d is a core orbital, we would rather have it full than our 4s orbital. So one just kind of slides over there. So just remember, chromium and copper and anything underneath them will end up having just one in the s orbital so that they can make their d orbitals more stable. So here it is. I've written it all out. So we have the elements in the D block, in that first level of the D block. Okay, so if you'll look, again, we're seeing irregularities where we have chromium and where we have copper. That's why one of our s electrons has slid over to the d orbital, again, because they're kind of similar in energy. So what happens here is we have, our unpaired electrons is really what we're going to be worried about in this chapter, okay? And it ends up giving us more unpaired electrons for chromium, and it doesn't really mess with our copper at all. If you'll look, though, zinc ends up having no unpaired electrons, which means that zinc can actually do some kind of cool chemistry. But I just wanted to include this here as a refresher in case you've forgotten how to fill orbital diagrams. So I want you to go ahead and write the condensed electron configurations for each of those elements or ions. Okay, so again, the condensed electron configuration, you're going to put your noble gas in brackets and then write the electron configuration starting from that noble gas. Remember what it means if something is, a 3+ ion, that means, it has done something with its electrons. Anyway, go ahead and try that out, pause, and then come back when you're ready. All right, so let's go ahead and go through this. So the first one we have zirconium, and zirconium is the second element in the 4D series. So it's the row below the one that we've been talking about. So instead of having argon in brackets, now we have krypton in brackets here. And then we have 5s2, 4d2, because it'll fill up the 5s electrons, and then it's the second one in that 4d. So nothing interesting happening there. It's not charged, it doesn't follow any weird rules, right? We're just going to write the electron configuration just like normal. Vanadium is the third element in the 3D series. So we would normally write it as argon, and then we would have 4s2, 3d3, right? Because it goes the 4s, and then it's the third one in the D block. But when it forms V3+, that means it's lost 3 electrons, right? So it's going to lose the 2 electrons from the 4s first, and then it's going to lose one of these electrons from the D block. And so then we will get argon and just 3d2. And then molybdenum is our last one, and it lies below chromium in group 6b. Okay, and remember, chromium was one of them that we had those exceptions where one of our D electrons slides over to the, one of our S electrons slides over to the D orbitals. So normally we would write it this way: krypton, 5s1, 4d5. So we get a half-filled S orbital and a half-filled D orbital with that irregular electron configuration. But when we have 3+ ion, we're going to lose our S electron, and we've only got one, so we're going to lose that one, and then we're going to lose 2 more out of our D block here, which makes it 4d3. So in this particular case, it wouldn't have mattered actually had you written the electron configuration originally wrong, because we're losing those 3 valence electrons. So unless I said, write it for molybdenum and then write it for what happens when it loses 3 electrons, I wouldn't have known that you did it wrong. But it is good to make sure that you're doing it correctly, just in case I do ask you for neutral molybdenum instead of the ion. All right, and so you may have heard this before, that most transition metals have multiple oxidation states. And we've looked at this when we studied ionic compounds, right? You needed to know whether, iron was going to be a 2+ or a 3+, right? Is it ferrous or ferric, right? And a lot of these transition metals can lose different amounts of electrons because they're not necessarily losing, all of their valence electrons. Okay, they're usually going to lose all of their S electrons, but the number of D electrons that they lose can vary. Okay, so that's why we end up having multiple oxidation states. If we're looking at the highest oxidation state, which is usually, for elements or for groups 3b through 7b, that's usually the oxidation state that they take, not always, but a lot of times, but it's going to match their group number. Okay, so group 3B starts with scandium, okay, and it goes all the way through manganese. Okay, and then obviously any of them below those. So the highest oxidation state for those groups will equal the group number. And this is because those elements tend to lose all of their valence electrons. Okay, so they just completely remove all of their D block, or all of their D elements, all of their S electrons, and they will use the noble gas configuration of argon or krypton or whatever came before them. Okay, this is typically seen when the metal is combining with something like really, really electronegative, like oxygen or fluorine, and that's when we're seeing all of those electrons come off. If we're looking at groups 8B, and so 8B is a little bit weird because it's groups 8, 9, and 10, okay? So this would be iron, copper, and nickel if you're looking at that first row of the transition metals, okay? So it's all of those, but elements of group 8B and then 1B, which comes after 8B, which isn't this great? So that's 11 and then 12. So this would be copper and this would be zinc, okay? But these elements have fewer oxidation states. They will have one that's pretty common and then some that are less common, but the highest oxidation state is usually less common, and it's never going to be equal to the group number. They don't lose all of these electrons. That would be a ridiculous number of electrons to lose. Normally what happens is they will form a 2+ oxidation state really commonly because they've lost their S electrons. They've lost their 4s or their 5s electrons. Those are the outer shell electrons. They're really easy to lose. So that's why we're seeing like copper makes a 2+, zinc makes a 2+, right? A 2+ oxidation state, super common. But otherwise, they don't really form a pattern. I've included this here. These are the most common. When we're asking for the most common maximum oxidation state for iron and cobalt, that'll be +3, and nickel, copper, and zinc, it's +2. So that would be kind of handy for you to have. But they can make other oxidation states. Like we know that copper is often a 1+, right? Iron can be a 2+, right? There are other oxidation states that happen, but it's when it's asking for the maximum common oxidation state, follow this. So here they are. The red dots, or the lighter red dots, those are the ones that are the most common oxidation states. Like I said, for scandium through manganese, that means they're going to lose all of their valence electrons. And then for iron and cobalt, like I said, they form +3s, and then nickel, copper, and zinc will form +2s. Again, there are other dots, right? Other really common oxidation states, but a lot of times if I'm going to ask it, I will ask for the maximum common oxidation state. Again, an oxidation state of 2+, if you'll look, like this 2+ row, that is really common because that just means that they're losing those S electrons. All right, I want you to go ahead and try this one. So pause here, figure out what the maximum commonly observed oxidation state of those elements is, and then unpause to see the answer. Okay, so for chromium is going to be +6. It's in group 6B, right? It's the fourth one over in the, in that first row of transition metals. So it will lose its 4 D electrons and its, 2 S electrons. It's going to lose all 6 of those and form a +6. Iron is going to form a +3. That's one that we were talking about that I said doesn't really form a pattern. But what happens is that iron loses its 4s electrons and then one of its 3d electrons, and it ends up having 5, half-filled d orbitals and then none in the 4s. Okay, again, a lot of times they're aiming for either completely filled or half-filled orbitals to be particularly stable. Cobalt is going to be from that previous slide. It's a +3. I would just know that one. Again, iron and cobalt and nickel a lot of times will form, iron and cobalt will form a +3. Nickel, copper, and zinc will form a +2. And then zinc, again, forms +2. It loses those 4s electrons, and then it has a completely full 3d orbital. So here it is. So this is kind of a different type of notation, this whole D1, D2. So if you're seeing that, or if you see that anywhere, that's telling you where the location of the last valence electron. So let's take scandium, for example. So neutral scandium has 4s2, 3d1. Okay, 4s2, 3d1 for our neutral scandium. So if it's, at this oxidation state of 0, right, it hasn't lost any electrons, then it's going to be d1 because it has 1 electron in the d orbital. But if it forms an ion, right, and the only one that it tends to form, it forms a 3+ or a +3. So what happens is it loses all 3 of these electrons. Well, when it loses all 3 of these electrons, it doesn't have any in the d orbital anymore. Remember, it'll lose those 4s electrons first, and then it'll lose 1 from the d. But what ends up happening is it's now d0 because it doesn't have any d electrons left. Let's look at zinc. Let's hop all the way down to zinc. So it's got 4s2, 3d10. So neutral zinc, or zinc with an oxidation state of 0, it has d10. There are 10 electrons in that d orbital. When it forms zinc 2+, right, so it'll have an oxidation state of +2, what happens is it loses these 4s electrons here. And when it does that, it hasn't lost any d electrons, so it's still d10. Okay, so again, all this is telling you, this notation is telling you how many electrons we have in the d orbital, or you can think of it as the location of that last valence electron. Where is that? So like I was talking about a bit earlier, most main group ionic compounds are colorless and diamagnetic because the metal ion has no unpaired electrons. So if we think about something like, let's say aluminum oxide. Okay, so this would be from aluminum 3+. Well, the way aluminum became a 3+ is it lost all of its valence electrons. And when it loses those, 3s and 3p electrons, it has a complete, underlayer, a complete electron shell underneath, because its electron configuration will be 1s2, 2s2, 2p6. Okay, all of those electrons, all of those orbitals are filled. They're all paired, right? We have all even numbers, and if we looked at the orbital diagram, we would have 1s, 2s, 2p, right? And it would all be filled. So all of these electrons are paired. And when our electrons are diamagnetic, right, when they're all paired up, we don't have any color usually associated with it. But the transition metals are different because a lot of times they will form ionic compounds, but they will still have some of these valence electrons in the d orbital. They don't lose all of them. And since they don't lose all of them, a lot of time they will be colored and they will be paramagnetic because they still have unpaired electrons. So that's the big difference here between main group ionic compounds and our transition metal ionic compounds, is we're getting unpaired electrons, and so we're getting these highly colored compounds, which is why we get all of the pretty colors. Like we were looking at on the previous slide, if you have anything that has D0 or D10, okay, so anything with like D0, all of these, right, or you have D10s, those are also going to be diamagnetic. All of those electrons will be paired, which means typically these compounds will be colorless. So here we go. Here's some pretty colors for you, right? I told you inorganic chemistry is so pretty. All of these transition metals make these great, beautiful colors. But when we have things that are forming D0 compounds like this one, right? Again, we're losing that color because we don't have those unpaired electrons anymore. So again, when we are diamagnetic, right? When we have all paired electrons, we're not seeing colors. But when we have things that are paramagnetic, right? They have unpaired electrons in those d orbitals, then we're seeing all of these pretty colors. And we'll talk more about why that is later in this chapter. All right, now I want to kind of switch gears and talk about complex ions. We've talked about complex ions quite a bit so far, and we've looked at reactions, that form them. But I want to look more at the complex ions themselves. Remember that complex ions are formed between in a Lewis acid base type reaction, right? We have these, lone pair electrons that are being donated to a metal ion. And in this, in this particular chapter, we're looking mostly at being donated to a transition metal ion. And remember, when we form those bonds, these are called coordinate covalent bonds. Okay, and we can think about them a lot like we do with regular covalent bonds because they're being held together by a pair of shared electrons. And for this reason, our complex ions don't dissociate in water because, again, they're being held together by a covalent bond. So this is not a transfer of electrons like an ionic bond. This is a shared pair of electrons, just like a covalent bond. All right, so now coordination compounds. So we've looked at complex ions before, where we have the metal ion and then we have the ligands that are attached to them. But a coordination compound is when we have a complex ion that's going to join up with some counter ions. Remember, our complex ions are ions, and so they're charged in solution, right? For example, this guy. Okay, so it's charged. Well, typically, when we're writing out a reaction, right, we don't include charged species normally. Normally, they are neutral species. And so what we do is we include some counter ions to balance the charge of that complex ion. So for example, right, this is a 3+, so it might join up with 3 negatively charged chlorines, right, chlorides, and form this coordination compound. Okay, so a coordination compound is always going to have a metal ion, right? And a lot of times this will be a transition metal. It's going to have some ligands, and then it's going to have some counter ions. Okay, so we're going to look at how these are formed. We're going to look at the ligands themselves, and later on we are going to learn how to name these coordination compounds, which is going to be awesome. So here it is, a coordination compound. This is a central metal ion, right? We have a cobalt ion there. We have 3 different ligands that are being attached, 6 different ligands that are attached to it. These are all ammonia molecules. And together, when we have the metal ion and the ligands, that's called a complex ion. Complex ions, like I said, are charged, so we are oftentimes going to include counter ions to balance out that charge. And when we put them all together, right, the complex ion and the counter ions, then we get a coordination compound, which is going to be neutral. So let's talk about the ligands. So ligands can be molecules or anions, right? Ions that are negatively charged, but what they have to have is 1 or more donor atoms. So they need to have an atom that has a lone pair of electrons. Oftentimes this is going to be something like an oxygen or a nitrogen. Those are the ones that are really common. Because they have that lone pair, they tend to be pretty electronegative, and they can donate electrons to that metal ion to form a covalent bond. We have a couple different types of ligands we have some that are not charged, which are molecules. We have some that are charged, which are going to be anions. They're negatively charged. But they can also be classified in terms of their number of donor atoms, or teeth, we like to call them. And the reason we call them teeth is we have this dentate that happens. So monodentate means that we have our ligand bonding through a single donor atom. So we have 1 atom on our ligand that is going to donate 1 lone pair of electrons to our metal cation. If we have a bidentate ligand, then it can have 2 different donor atoms. So it's not the same atom donating 2 different pairs of electrons. It's going to be 2 completely different atoms, maybe an oxygen and a nitrogen. And each one of those atoms will donate a pair of electrons to the metal cation. And then we can also have polydentate ligands, which means that they have just more than 2 donor atoms. Okay, so we're going to look at those. So this is ethylene diamine, which we oftentimes will abbreviate EN so that we don't have to keep writing it all out. But this is a bidentate ligand. And so what happens is each one of these nitrogens donates a pair of electrons to the metal atom. Okay, monodentate ligands are what we had looked at previously in previous chapters, where it's like hydroxide or ammonia, maybe water, things like that. That would be monodentate. But when we have ligands that can form 2 bonds, like ethylene diamine, that would be bidentate. Again, they always have to be on separate atoms. And usually these atoms, right, like these 2 nitrogens, see how they're not right next to each other? Oftentimes they'll be 2 atoms apart like we see here, or they may even be 3 atoms apart, but they can't typically be right next to each other because the bonds can't really reach around to coordinate to the metal atom. So here's some examples. So we have monodentate. Those are the ones that we've worked with a lot thus far. Again, like water, ammonia, cyanide, hydroxide, right? Those are really common. For bidentate, we have ethylene diamine and oxalate. We've worked with oxalate before, not really as in a ligand, but in ionic compounds. And then polydentate just means that they have more than 2 donor atoms. So we have diethylene triamine, we've got triphosphate, and then we have EDTA, which we'll look at a lot. And EDTA actually has 6 different atoms that can donate to the metal cation, which allows it to do some really cool chemistry. So here's EDTA. Again, it is hexadentate, which means it has 6 different atoms that will donate electrons to our central metal atom, which is pretty cool. So our coordination compound, right, is made up of our complex ion and our counter ions. And when we put this into water, the counter ions totally leave, right, because this is ionically bonded. So this guy is positively charged and this is negatively charged. We're not sharing electrons here. This is a transfer of electrons. These are complete charges. So when we put this into water, right, this coordination compound into water, those bonds break. The chlorides leave and we're left with our complex ion. The complex ion, though, remains together. Those 6 ligands, those 6 ammonias will stay on that cobalt because those are covalently bonded. Similar in this one, right, we have the potassiums will come off because those are, that's our positive charge. This is our negative charge. So the potassiums come off, they leave, but those 4 chlorides will stay bonded to the platinum. Okay, so when we dissolve these in water, all of the ligands will stay attached to our metal cation, but the counter ions will, float away. So the reason that we care about this is because we look at coordination numbers. And the coordination number will tell you how many ligand atoms are bonded directly to the central metal ion. So this is not including any counter ions because the counter ions have, like I said, kind of floated away. So we're just looking at the ligand. And I want to note that I underlined the word atoms because sometimes we will have bidentate ligands and those will have 2 atoms that are bonding directly to the central atom. Okay, so you can also think about this as the number of bonds maybe that are going directly to the central metal atom. So like how many bonds are being formed total between the ligands and the metal. And so coordination numbers are specific for a given metal ion in a particular oxidation state, in a particular compound, right? And so we often need to know the formula of our complex ion. So here, if we're looking at this, ammonia is a monodentate ligand, which means it's just making 1 bond with the chromium. So since we have 6 ammonias, each making 1 bond, we have a coordination number of 6 because there are 6 bonds going to the chromium. A lot of times, we'll see 6 as our common coordination number, but you might also see 2, 4. You can also see odd numbers too. Even numbers tend to be a little more common though. So I want to go ahead and practice. So we have some coordination compounds here. So again, they have their counter ions and the complex ions, but I want to know the coordination number of the metal ion in those coordination compounds. Okay, so you need to figure out, first off, which part is the complex ion? Big hint, complex ion is usually the part in brackets. And then from there, figure out how many bonds are being formed to the metal ion. Not necessarily how many ligands total, right, but how many bonds total. So I want you to go ahead, pause here. May help you to look at that chart that said the monodentate, polydentate, and bidentate ligands. That may help you. But pause here, try it out, come back when you're ready. All right, let's go through this. So for the first one, right, we have sodium and then we have this zinc bonded to 4 hydroxides. So each one of the hydroxides is monodentate, which means that it's only making 1 bond with the zinc. So since there are 4, each making 1 bond, our coordination number is 4. For the next one, we have 2 waters, which are each monodentate, So we'll get, one bond from each of those. But then we have 2 oxalates, and each of the oxalates are bidentate. So we end up having, 2 times 2 from the oxalates plus our 2 times 1 from the waters. So our coordination number is going to be 6 overall. For part C, we have, again, 2 waters, each one's monodentate. We have 2 ammonia, again, each one monodentate, and then 2 chlorides, again, each one monodentate. So even though we have a bunch of different ligands, each one is only making 1 bond. So we have 6 ligands total, so our coordination number is 6. Our last one, I wanted to include this one because it has the abbreviation here. Anytime you're seeing EN, that's standing for ethylene diamine. So it's so we don't have to just keep writing that over and over. And the writing the structure wouldn't really help us either because it's still just as long. So EN is what we use for ethylene diamine. That is a bidentate ligand. So each one is going to make 2 bonds, and we have 3 of them. So our coordination number is 6. So last kind of topic for today, when we have bidentate and polydentate ligands, they will form rings with our complex form rings in our complex ion. So the way that they coordinate to the metal, right? If we look, this is ethylene diamine up here. Okay, and so we've got our nitrogen making a bond here and our nitrogen making a bond here. And like I said before, they're usually going to be separated, those 2 nitrogens, by a couple different atoms. And the reason that they're separated by a couple different atoms is so that they can make these rings. You'll find as you go forward in chemistry, especially if you take organic chemistry, you're going to see that molecules and compounds like to form rings. They tend to be really stable in forming rings, especially 5-membered rings or 6-membered rings. Those are really stable. So here we have a 5-membered ring. We go 1, 2, 3, 4, 5. And again, like I said, 6-membered rings are also really stable. So this is what's called chelating. So we call it chelating because it looks like this this ligand here is, biting onto the cobalt. It's using its teeth and it's latching onto the cobalt. Okay, or you can think about it as having claws. EDTA has 6 donor atoms and it forms really stable compounds with metal ions. So if you look, so here's our lead, and it is forming 6 bonds. So it's got 1, 2, 3, 4, 5, 6. So that whole monstrosity is 1 ligand. That 1 ligand has made 6 bonds with the lead. And it's actually really cool. EDTA is used as a treatment in lead poisoning because it can do this whole grabbing onto the lead. So if you happen to have lead poisoning, EDTA can be used as a treatment because it will go through the body, it will find lead, and it will use its metal claws or its teeth, and it will bite onto the lead, and it can be removed from your system. It's really cool. So here you go. Here's some more complex ions with polydentate ligands. So we've got cobalt being bonded to ethylene diamine again. So we've got 1 bond here and 1 bond here. And then for a different ligand, we've got 1 bond here and here. And then we've got 1 here and, it's kind of back there. And then cobalt on the right is bonded to EDTA, so it's got 6. So it's got 1, 2, 3, 4. It's got 1 going down here, 5, and then 1 up here, 6. So again, that's 1 giant ligand that's bonded onto the cobalt on the right, and it's got 3 ethylene diamines over here on the left. Both of these, though, have a coordination number of 6, and like I said before, 6 tends to be kind of common. And that's it for today. So this was an introduction to chapter 25. We covered a lot of information related to transition metals and started getting into our work on complex ions and ligands and coordination compounds. We will look more at coordination compounds and specifically how to name them during the next chapter. So make sure you have a good idea of how to identify the oxidation state of that metal and how to identify its coordination numbers. Those will be important in the next lecture. So make sure, you're reading the chapter and going through those lecture worksheet problems and getting all of the practice you need to feel confident about chapter 25. Keep working hard. Send me any questions you have. And otherwise, I will talk to you guys next time.